All right, according to the clock up here, it's 10:15, so why don't we go ahead and get started on time. Good morning, everyone. I'm Rick Fienberg, AAS Press Officer, and we're here in San Diego, California for the 228th meeting of the American Astronomical Society. I would like to ask everybody here in the audience to please silence your electronic devices. The way our briefings work, if you haven't been to one before, is I'll give a brief introduction to the topic and I'll introduce our speakers, and then they'll each speak in succession and we'll hold questions until the end. I want to remind everyone that we're webcasting the proceedings, and so when it does come time for Q&A, you'll wait for a mic so that the people on the webcast can hear what you're saying. And if you're on the webcast and you have any problems with the feed, please use the text chat to report the problem. My colleague Mike Zevin from Astrobytes is monitoring the webcast, and he'll relay any issues to our tech team. Okay, well, this morning we have three speakers, but it's actually two papers. The first paper is appearing in Science today by special arrangement with Science and the AAAS. That's why the Science and AAAS logos are on the podium this morning. I'm very grateful to my colleagues there for making it possible for us to have this briefing today by moving up their publication. So Brett McGuire from the National Radio Astronomy Observatory and Brandon Carroll from Caltech will talk about life's first handshake, discovery of the interstellar chiral molecule propylene oxide. Okay. And then they'll be followed by Joel Green from the Space Telescope Science Institute, speaking on the evolution of FU Orionis disks. Now, these papers may seem somewhat unrelated, but actually there's a theme running through it having to do with interstellar medium, chemistry, star formation, planet formation, and so on, as you'll see when you hear the results. So Brett and Brandon are actually co-first authors on the science paper that's being published today online. There are press releases for both of these results. A couple of them went out under embargo. The rest will go out in just a few minutes. And so there'll be lots of good reference information. So with that, I'll turn it over to Brett, and we'll get started.
All right, well, thanks, Rick. Brandon and I are really excited to tell you guys today about our discovery of the first chiral molecule seen in interstellar space outside our solar system. This molecule is called propylene oxide. We discovered this molecule in a massive cloud of gas and dust in the galactic center called Sagittarius B2 North. And as you're going to hear about over the next few minutes, this is going to provide us with a laboratory to try to test theories about the role that chiral molecules played in the origins of life here on Earth, and how that chirality might play a role in the origins of life elsewhere in the galaxy. So a little background now. I use the word chirality and chiral molecules. What is that? Well, chirality, chiral, comes from the Greek word for hands, and that's because your hands are a really great example of two things which are chiral. Right? Your hands are mirror images of one another. Right? But they're not exactly identical. If you try to line your hands up on top of one another, your thumbs are facing two different directions. Right? Now, if you line them up so your thumbs face the same way, the palms are facing different directions. Right? So they're non-identical mirror images of one another. Chiral molecules have the same property. They're all the same atoms bonded together the same way, but they're mirror images of one another, and there's no way you can rotate or translate these molecules in space and line them up exactly. Different versions, these different mirror images of one another, are called enantiomers, so it's a word that we'll use throughout the rest of the presentation. Now, what makes these interesting? Well, enantiomers have interesting properties. They have mostly the same physical properties. It means they have the same elemental composition, the same atoms bonded the same way. They have the same melting, boiling, and freezing points, and they have the same what we call rotational spectra. This is the frequencies of light that the molecules absorb or emit as they tumble end over end, in this case in interstellar space. How they're different is the way that they physically interact with things, right? So just like when you shake somebody's hand, your right hand shakes another right hand, and it forms that nice interlocking gesture. If you try to shake a left hand with your right hand, it's a little awkward, right? Because the interaction is different, and chiral molecules work the same way. Now, this introduces some interesting things in biology. For instance, one of the best examples is this molecule carvone. It's in the upper right-hand portion of the slide, right? And the two enantiomers of carvone interact with your smell receptors and taste buds in different ways. One of them produces the taste and smell of spearmint from mints, and the other one produces the taste and smell of caraway. It's what gives rye bread its distinctive flavor, right? They're the same atoms bonded the same way. They're just mirror images of one another, and they give you a completely different sense. This translates all the way to biological functions as well. So a lot of drugs will work for one enantiomer, but not for the other. But most relevant to what we're going to talk about today in the origin of life is the way that life incorporates chiral molecules into the building blocks. So your proteins are all made up of amino acids. They're Legos clicked together in a row to build up these proteins. And all of these amino acids that are chiral are left-handed in life as we know it. Similarly, most of the sugars that life uses are right-handed. They're D sugars. Now this is interesting and useful for building up more complex structures. So if life used a mixture of both left and right-handed nucleobases, say, there's no way that you could build up that double helix strand to the DNA. That is due to the fact that we use only a single version of each nucleobase to build up that complex structure. So it's very beneficial to life to build up these more complex and useful models of chemicals. Now, the big mystery, though, is why we use left-handed amino acids instead of right. All of those large structures could be built up the same way using the other enantiomer, right? And they'd work the same way. So why does life use exclusively one and not the other? This preference for just one is called homochirality, and it's a big mystery in the origin of life. There have been a lot of theories over the years about where this could be coming from. Some theories look at the selection of one enantiomer to be used in homochirality early on the development of the Earth, say down near the hydrothermal vents in the early ocean. But more interesting to us is going even further back in time and looking at if there's a way for the scales to be tipped towards one-handedness over the other, all the way back in the primordial molecular clouds where molecules started to form. And I'm going to turn it over to Brandon to tell you about how we looked back into time into one of these molecular clouds to search for a chiral molecule.
Right, thanks. So what originally piqued our interest in understanding the origin of chirality were studies of meteorites and comets. So these are pristine records of the earliest parts of our solar system. These are rocks that were formed roughly the same time the Earth was. They were made out of the same material that our solar system formed from, the same cloud of gas and dust. And very interestingly, there have been a lot of complex molecules found in these bodies. These include a lot of the basic building blocks for life, including purines, pyrimidines, sugars, and very interestingly, amino acids. And one of the most interesting things that's been found, particularly in this meteorite Murchison, is that not only are there an abundance of amino acids, over 80 amino acids found, that these amino acids are shown to have a preference, a small, only a few percent difference, but a small excess of left-handed amino acids. And that's very interesting because that's the same preference that biology shows. Now, in biology, homochirality is 100%, but there's an interesting link here because if, say, even a few percent excess in one amino acid was delivered to Earth, and we know that the Earth accreted a substantial amount of material, water and organics, from bodies like this, if even a small percent excess was present in these, this could be the tipping point that pushed life in a single direction, and that gave life the push it needed to, say, use only left-handed amino acids. And so we're very interested in this, but if we want to understand where and how this started, we have to go back even further than the meteorites. We have to look at the gas clouds where these molecules formed from. And so if you want to detect new molecules in space, the place to do it is Sagittarius B2 North. It is a powerhouse for detecting new molecules. Of the roughly 180 molecules detected in space, over a third of them have been detected in Sagittarius. Often they are first detected in Sagittarius and then found other places. So this is the best place in our galaxy to find new molecules. In fact, it's been so good, there's been an ongoing survey with the Green Bank telescope for the last decade to survey Sagittarius in the radio regime and use this data to detect new prebiotic molecules. So Brett and I actually started working with this project about 4 years ago, in a general sense, helping to take and reduce the data. But we were interested in looking for chiral molecules, so we started going back through the data, looking for signatures of possible chiral molecules, and that's what we found. So this is the molecule right here, propylene oxide. It's 3 carbons, an oxygen, and 6 hydrogens. And in the top 2 panels on the left, you can see the 2 initial signatures we found of propylene oxide. These are absorptions. It's, as Brett explained, these absorb at very specific radio frequencies, and this is propylene oxide absorbing against a very bright continuum towards Sagittarius. And this is very promising. It's an indication that the molecule is there, but we wanted to be very sure that we'd actually detected a chiral molecule. So unfortunately, the other possible transitions we wanted to target are not observable from the GBT. The GBT sits in the National Radio Quiet Zone, but that doesn't actually protect you from satellite interference. So the third and final transition is actually obscured by satellite radio frequency interference. So to get the last transition, we went to the Parkes Radio Telescope in Australia, and you can see the last signature down in the bottom right. So that's it. That's all 3 of the expected transitions we've seen. So now we feel like we have actually detected this molecule. So I should say that these observations aren't sensitive to the handedness of propylene oxide. We know that we've detected the molecule, but I can't tell you if there's more right or left-handed propylene oxide. And so that's where we want to go from here. So this is the initial detection to prove first that chemistry in the interstellar medium can actually make chiral molecules. And now it gives us a test bed, some molecule we can actually go back and perform the far more complicated and challenging observations necessary to detect the handedness. And so that's where we're going to be going from here. We're going to be working to actually detect an excess of one of these. And that's what we're really excited about, because that'll let us start to test theories about processes that might actually have chiral preference in the interstellar medium. So that maybe something like circularly polarized light in space actually preferentially destroys one-handedness of molecule over another, and that imprints a preference on all the material formed in that cloud, and that is transferred to meteorites and eventually planets, and that can have an influence on the handedness of life that we see in that system. So that's what we've done, and that's where we're going to be going from here. So thank you all very much for listening.
It's all good. Hi, everyone. So I'm Joel Green. I'm the project scientist in the Office of Public Outreach at the Space Telescope Science Institute. And I'm going to tell you about an interesting discovery monitoring the FU Orionis disk. So when young stars form, they form out of clouds of gas and dust that collapse under the weight of their own gravity, and you end up with sort of a proto-sun type system surrounded by a disk of gas and dust, like the one pictured here, swirling around and heated internally. And that is the system in which, in the earliest days, the gas giant planets and then later the rocky planets will form. One of the things that's interesting is whether this process is as smooth as I've just described it, and there are a few signs that this is not the case. A star called FU Orionis, and it's so named because it's in the constellation Orion, it's actually in the shoulder of Orion, erupted in 1936. It was observed previously just on photographic plates, and then people noted this rapid rise by a factor of almost 200 in its brightness in the 1936 to the beginning of 1937, marked with the blue shaded region there. So this is a plot of the brightness of F Orionis in 1936 with a gigantic rise and then a gradual decay that's been very steadily but slowly continuing to this day, so that by 2000 it was about a factor of 3 fainter than it was at the peak of the burst. But nonetheless, very much still in an excited state. And what scientists thought at the time, and still think today, is that F Orionis had undergone a burst accretion event. That is, the inner portion of the disk had accumulated so much material that a gigantic amount of it started cascading in. And over the past 80 years, judging by the brightness of F Orionis, it has accreted approximately 18 Jupiters worth of material in that time. A substantial fraction of the disk that is surrounding it, as we discovered more recently. Now, I'm particularly interested in what effect something like that might have on the disk, which is right before the epoch of planet formation. So this is a very interesting question. Now, this is a movie produced by Robert Hurt at the Spitzer Science Center, IPAC. The idea is, if a huge amount of material were to fall into the star, there would be a massive heating event, and the inner disk in particular, but the entire disk as a whole, would be cooked and its temperature elevated very quickly. That would have irreversible chemistry changes, or could at least have irreversible chemistry changes. And so we could look for signs of the components changing properties throughout the burst. And this has been seen in very short-term bursts, but we were trying to look for changes in the F Orionis system, which is it's actually the most dramatic burst ever seen in a sun-like star like this. And it was also the archetype. So F Orionis, I should say, is rare, but is not unique. There is a small class of these objects. So this is just the archetypal object and probably the most dramatic of them. So this, I'll take a moment to explain, this is the data. So one of the neat things is that in order to probe circumstellar disks, you really need infrared light. And in particular, you need spectroscopy in the infrared. And there have only been, to this day, 2 major observatories with infrared spectrographs sensitive enough to detect and measure F Orionis. And those are the Spitzer Space Telescope's infrared spectrograph and the SOFIA's forecast instrument. So Spitzer on the left was launched in 2003, and is a NASA satellite. It's still operating today, but the infrared spectrograph has not been operating since 2009 when the coolants were depleted. And SOFIA Forecast is a NASA airborne observatory that launches out of Palmdale, California, which I flew on. The data from Spitzer was taken actually in my very first interaction to graduate school, so it's an interesting sort of loop back around to my original paper. 12 years later, we will compare it with the forecast data on the flight that I made in February. In this plot, we're plotting the power of F Orionis, or the energy output, as a function of wavelength or frequency. So to the left is the hottest material, and to the right is the coldest. This overall shape you're seeing is all driven by the emission from the disk of F Orionis, which is actually so bright that it massively overwhelms the central star. So what you're seeing, everything here is attributable to the disk. Now the red, I've color-coded this. The red are observations from around 2004 or slightly earlier, or slightly later in a few cases, and the black are data taken this year. The red points are from various observatories or imaging, and then the red spectrum is the Spitzer IRS spectrum that we took back in 2004, whereas the black line is the forecast, or various pieces of the forecast spectrum. And I show them for a comparison. Now, on this scale, it doesn't look like there's a dramatic change, but I've put together a red and a black model. The black model is simply decreased by 13% over the red model, and you'll see that they fit the data very well. So what we discovered is that particularly in the visible and near infrared, out to about 8 microns, F Orionis power output has decreased by 13%. Then there's a short transition region, but by the time you get to about 20 microns and beyond, the coldest material, there is no detectable change in the F Orionis disk. So what does that mean? So hot material has decreased, cool material has not. If you zoom in on a portion of the spectrum, the shorter wavelength part, you can see this transition a little bit more clearly. If you look at the left end of this plot, you can see that the red and black lines are more divergent than they are on the right side. Again, the red line is the Spitzer spectrum, and the black line is the higher resolution but higher noise SOFIA spectrum. So the wiggles are noise, but the shapes are real. And you can see not only is the shape maintained but lower, but in addition, the little bumps, the two absorption features on the left due to water vapor in the atmosphere of F Orionis's disk, which is at about 12,000 degrees, and the bump from the silicate dust is still there. So what do we think has happened? So this decrease only in the hottest material implies that we've removed about 13% of the hottest material. So in this artist's conception, you see the F Orionis disk. The hottest part in 2004 is extremely bright, leading out to a cooler disk. And in 2016, you can see that the inner portion has decreased in brightness and perhaps in material, but the outer disk remains unchanged. Now, there are two explanations for this. One possibility is that the central region has cooled. And we do not yet have the sufficient data quality to rule that out. So that is still a possibility. The temperature could have cooled down to about 5,000 degrees and from 7,000 Kelvin and still be consistent with our data. The other possibility, and the one that I favor, is an alternate hypothesis in which the material in the innermost region continues to accrete onto F Orionis and has depleted, and that therefore that's what's driving the burst in the first place, and 13% of that material has diminished. So this is an inside-out cascade into F Orionis. To really nail this down, however, we would like to observe this in the future with the James Webb Space Telescope, which can really nail down this slope and measure dust properties a little bit more carefully. So the reason this is interesting to me is what is the future of the F Orionis disk? If we wait a few hundred years, it will have cooled back to its original brightness. This is analogous to something that could have happened here. If these objects are common, if this kind of event is a key phase in star and planet formation, then we need to know what lasting effects that leaves so we can look for signatures of this in our own solar system. For example, there is a noted depletion of volatile lithophile elements in Earth that is not at Mars. And that is consistent with the kind of temperature variations you would get during an F Orionis burst. It's not the only explanation for that, but it's consistent with that idea. During a burst such as if our sun were to do this, the temperature around Earth would suddenly become about 1,000 degrees Kelvin, or about 1,500 degrees Fahrenheit. And the innermost area beyond Mercury would rise to 12,000 degrees Fahrenheit. So clearly this could have some very interesting effects, and it's worth looking into. And I'll just leave up my summary of points, and thank you very much.
All right, thanks very much. So we'll first open it up to questions from here in the audience. I'll remind you to wait for the microphone and identify yourself by name and affiliation, and make sure you let us know who you're asking your question of. And then we'll take questions from the web. So we'll start here in the room. Questions? They were clear, but they certainly left some things open. Yes?
Thanks. I'm Steve Blau from Physics Today. And I think, Brandon, you mentioned that the exciting stuff is yet to come when you try to determine if there's a favorite chirality out there. Can you tell us how you're all going to go about doing that?
Sure. So the idea is to do what are called polarization-sensitive observations. So as Brett was explaining, chiral things really separate themselves when they interact with other chiral or handed things. And so the only really good way we can think of to distinguish handedness in space is by how they absorb polarized light. So light can be handed. Left or right circularly polarized light can be absorbed. So say you had a right-handed propylene oxide molecule, it would preferentially absorb more right-handed polarized light. By going back to the Green Bank telescope and actually doing the measurement where you measure how much of left and right circularly polarized light is absorbed, you can back out how much of each handedness there is.
Can I follow that up just a second?
Yeah, keep the mic.
Yesterday we had a press conference, and the gentleman who spoke yesterday was interested in polarized electrons. Is there any possibility of exploring the effect that electrons in the interstellar medium might have?
Sure. So there was actually a really exciting result this last fall that came out relatively definitively showing that beta decay, which produces electrons throughout the universe, those electrons come out polarized, and they will preferentially destroy one-handedness of a molecule over another. that effect would be fairly universal in nature, or universal in nature, happening everywhere. The interesting thing is the balance between that effect and what would probably be the larger but localized effect of circularly polarized UV light, which would destroy more molecules, but not necessarily the same handedness as those electrons. So you could get localized pockets, perhaps, of one-handedness or the other being in excess. But that destruction by those electrons is certainly a method, and the paper came out this fall in PRL, I think.
I think what he's saying is that, you know, on the one hand it could be polarized this way, and on the other hand it could be polarized the other way, right? I had to say that. I was surprised one of you guys didn't.
We were setting you up.
Thank you. All right. More questions from here in the room? All right, Mike, do we have any questions coming in online?
Nothing online yet.
Nothing online? Boy.
Can I ask a really dumb question?
No, you can't ask a dumb question. There are no dumb questions, but you can ask another question.
So I think you said that, I think Brett said that the amino acids were left-handed and the sugars were right-handed. Doesn't matter if I got that. Is there any absolute meaning to that? Could I say the sugars are left-handed and the amino acids are left-handed? It's just that they're handed, right?
I guess well, the trick is that they're all one-handedness. So that's the big thing, is that they're all left-handed or they're all right-handed, and that's what is really key to building big biological structures like the DNA helix. But you could imagine a mirror image world where everything looks exactly the same, but all your amino acids are right-handed and all the sugars are left-handed.
But once you get something that's super complicated and you know it's not the same as its mirror image, how do you decide if it's left or right?
There are standard internationally recognized conventions for the way it's very complicated, and it annoys a lot of undergraduate chemistry majors trying to go through and make sure they've got the handedness right. There's a huge priority system for assigning these things.
Okay, we have one in the back.
Hi, this is Ryan Lau from Caltech and JPL. I have a question for Joel. If you're removing material from the inner part of that disk, wouldn't you expect the dust to be hotter, since you're sort of removing any sort of opacity sources?
Indeed, in fact, during the burst, the dust in that region, the region that we're talking about, would have been destroyed at the very beginning of the burst. So in fact, the opacity sources are gone.
I mean, but the dust that you're seeing that seems to not have changed, wouldn't you expect that to be hotter?
I'm sorry, the dust that we're seeing that has not changed comes from farther out in the disk. That is at 300 degrees Kelvin. So that is, the reason it hasn't changed, I think, is that it comes from, say, a few AU. So this is dust that is settled out in the part of the disk that is not changing very much, even in the continuum. So actually, the fact that the excess has not changed, that the long wavelengths has not changed in terms of continuum, is consistent with the idea that the dust that's producing that 10 micron silicate dust feature has not changed. It's also consistent with the idea that the water vapor that is producing the absorption features at slightly shorter wavelengths has also not changed very much. It's sort of in the transition region.
Thanks.
I actually have a question for you as well, Joel. You showed the light curve. That was visible light, right?
That was visible.
From 36 to present. So is the fading in the visible light curve consistent with the changes that you're seeing in the infrared?
That was probably one of the most encouraging results, was that the fading in the B band, the visible light, was 13%, and the fade in the infrared was between 12 and 13% in the shortest wavelengths, and then it decreases to 0, essentially, as you go to longer wavelengths. So, in other words, the hottest material that we're observing with Sophia and Spitzer is changing very consistently with the visible end of the spectrum, which is all the hot stuff. So the stuff that's at 6,000 degrees, that is dropping. The stuff that's at 1,400 or less is not.
And what kind of star is it at the center?
So we don't know exactly, because it's been hammered by all this stuff, but we believe that it's something probably about a half a solar mass central, or maybe 0.3 solar mass central star. So but it's a little hard to define because it's still a protostar, it's still growing, but it's going to turn into something likely a little bit smaller than the sun.
And you also,
and it's young, and it's only a few 100,000 years old, so it's still, at this point, it's probably quite puffy, probably 3 or 4, maybe even 5 times the radius of the sun.
okay, so it's still collapsing into its main sequence state.
That's right.
But
It's not only is it's very early in that process.
And you mentioned also that if we waited a few hundred years, we would see it drop back down to its 1936 level or before that. Um, is that based on the current rate that you're seeing the decline? But the visible light looked like it was really going slowly. It didn't look like it. It looked like it was going to take a much longer time to get down to its pre-outburst level.
That's an extrapolation based on the visible light. So at some point you start dropping back into the region where you're indistinguishable from the disk.
Okay.
So the visible light is currently dominated by the disk's brightness, but at some point when the disk fades to not being the dominant source, then the star will take over that part of the spectrum again. So, but it's quite long. The other thing is that although FU Orionis is the archetype, one of the differences between the different FU Orionis stars is the rate at which they decay. There's another star in Cygnus called V1057 Sig that is decaying at something like 3 times the rate of FU Orionis. So there is some variability in these bursts.
Okay. Are there any other questions from here in the room? Any come in online while we were talking? We got a question online, okay. Please let us know who's asking it.
Yes, this is from Irene Klotz from Reuters and Discovery Communications. Irene's asking a question for Brett and Brandon. Just to be clear, is it the detection of propylene oxide itself that implies a chirality?